So now let's talk about multivariate functions. So let's say your function is a function of two variables. Y is equal to ax1 square plus bx2 square. Right. So what does that function look like? Assuming a and b both are greater than 0. Right. So I need to draw x1 and x2, but where does y go? How will I draw y? So let's try to draw this. Let's say this is x1 and this is x2, right? And what we will do is we will draw this as a contour plot. Okay, so these will be contours. Contours means we will look for constant values of y. So let's say x1 is 0 and y1 is 0. Sorry, x1 is 0 and x2 is 0. Then what we'll get is y is equal to 0. Now let's take another uh, value, another constant value of y, and find all the entire locus of x1 and x2 for which we get a constant value of y. So that locus is going to be some elliptical shape. So I'm assuming that this elliptical shape is elongated along x1, but it need not be. It could be equally elongated along x1 and x2, or it could be more elongated along x2 or something like that. Um, so let's say this is for y is equal to 1. Similarly, we'll have something for y is equal to 2, okay? And then we'll have something for y is equal to 3, etc. Okay, so we'll have these something called contours or level sets. Contours or level sets. That's the way to draw it. So basically think about it this way, that this is like a bowl, and the bottom of the bowl is at x1 equal to 0, x2 equal to 0. So this is the bottom of the bowl. Minima of the bowl. And the bowl rises as you increase either x1 or x2. Clear? If a and b were both less than 0, then the bowl would be inverted and this would have been the maxima. And the bowl would be curving away from you into the screen. Right now the bowl is curving towards you outside the screen. Okay. So keep these contours in mind because we will use them again and again. So this is a multivariate function. So now this multivariate function can, even like with two variables, can have different shapes, right? So even if it is like a bowl, this bowl need not be axis aligned. So for example, this bowl could be tilted. Okay, or this bowl could be somewhere else. So these are all convex functions, but let's say it need not even be convex, in which case it will have, the contours will have complicated shape. They will not look like ellipses. But this is just for simplification. We have chosen this because we will be, for a lot of times, we'll be assuming even if the function is not globally convex, we will look at the local behavior, and whichever is the closest bowl that fits to it, we will worry about that. We'll basically analyze that. So now, what does a derivative mean for a multivariate function? So here, when we had y is equal to ax1 plus bx2, right? Ax1 square plus bx2 square. We can't just define a derivative with respect to x1. We have to define the derivatives, partial derivatives, separately for the two functions. So we'll have del y by del x1, okay, and del y by del x2. Okay, so let's make this into a vector, and this becomes, so if you take the partial derivative with respect to x1, you will hold x2 is equal to constant and it will disappear. So it will be 2ax1 and 2bx2. Okay. So at any given point x1 and x2, we have a vector of two dimensions, which is given as follows. So what does that vector mean? Okay, so let's draw this out. Okay, so now let's take a point x1 and x2, right? So there's a 2ax1 and 2bx2. So that's a so if we look at this vector, right, it is actually pointing in some direction. Okay, so it has a component which is 2ax1 and it has another component which is 2bx2. Okay, so these are the two components of this vector. So it turns out that this vector is going to be at a 90-degree angle to the tangent at this contour. So it's a normal vector to the contour and it is pointing outwards away from the local minima. Okay, so it turns out that at any given point, this is the direction. If I make it into a unit vector, it will become a direction of steepest what, descent or ascent? It is ascent. Okay, so this now gives me insight into uh, minimizing. Let's say if I want to minimize the function, I want to find x1 star and x2 star that give you the minimum value of this function f of x1 and x2. So let's say I call it f of x1 comma x2. Right, so this is the function, multivariate function. So now the update equation for me will be a generalization of what we saw earlier. Okay, so x2. Okay, so we will reassign it the old values. So these are the old values minus eta times uh, del of y by del x1, del of y by del x2. Okay, or in other words, we call this as gradient of y with respect to x. Okay, so it will be we will subtract eta times the gradient of y from the original values of x1 and x2 to get the new x1 and x2 to take a small step in the direction opposite to uh, the gradient. We will take this step and then this step and then this step and this step until we reach the bottom of the both. In gradient ascent, it will be opposite, and the sign here instead of negative will be positive sign. So the gradient, the dimension of the gradient is same as the number of variables that we have in the function. Now let's look at Newton's method for multivariate function, which is basically asking ourselves how can we scale this gradient descent so that we take only one step if we want to reach the bottom of a perfectly convex function or a perfectly second order function, not perfectly convex but perfect second order function, where the second derivative is constant. Now before that, let's ask ourselves what does second derivative mean. So we know that if we have a function of x1 comma x2, right, then basically there is no such thing as f dash of x. What we will call it as, we will call it gradient of f, right? This is going to be del f of by del x1 and and del f by del x2. So it's going to be a vector like this, right? So now there is something called the second derivative of x, which we will call as Hessian of x. Okay, so this Hessian is going to be a 2 by 2 matrix. It's no longer going to be a scalar or a vector, the second derivative. So basically what we have is we will have del square of f by del x1 square. Okay, these will be the diagonal terms. Del square of f by del x2 square, right? And then the off diagonal terms will be the this del of f by del of x1 del of x2, del of f by del of x2 del of x1, the second derivative with two different variables. So once you will hold x1 constant, the other times you will hold x2 constant. Um, sorry, the notation. So basically it has the diagonal terms are essentially the same because the order of the derivative is interchangeable. Uh, the off diagonal terms, sorry, the off diagonal terms are the same. So in general, if you have n dimensional uh, functions, right, functions of n variables, your matrix will be such that the ijth term would be del square of f by del xi del xj. Okay, this will be the general term. Okay, where the off diagonal term, the diagonal term will be the double derivative with respect to just double partial derivative with respect to just one variable. Um, so let's take a look at what that looks like for, let's say, a x1 square plus b x2 square. Okay, so your h is going to be so this was 2a 2a x1, so it will be 2a 2b, right? And then the diagonal terms would be basically 0 and 0 because you will take the derivative with respect to the other variable and that will not pan out. Okay, that will be 0 because that variable is not present. So what does this mean? So basically this second derivative tells me that so if I take the eigen analysis of this second derivative of this Hessian matrix, the eigenvectors tell me the direction, the eigenvector corresponding to the highest eigenvalue will give me the direction of the steepest ascent. Okay, and if I have a positive eigenvalue versus negative sorry, the gradient tells me the direction of the steepest ascent. Uh, Positive eigenvalue tells me that there is a uh, uh, in the direction of the eigenvector there is a minima, the function is decreasing, and uh, the negative eigenvalue tells me not that it is decreasing, the derivative is increasing, and the other side tells me the derivative is decreasing. I'll explain it better when we actually talk about second order optimization later for neural networks. Um, for now, just let it be like this. Uh, but suffice it to know that if I want to do Newton's method for multivariate functions, then my x vector will be updated as x vector, okay, minus h inverse gradient. Okay, so this is an n by n matrix. This is an n by 1. Okay, so it will become n by 1, which is what this is also n by 1. This is also n by 1. Okay, So now here the problem is that I need to take a square matrix, and the square matrix need not be a diagonal matrix, and I need to invert it. Okay, so this operation is order n cubed. With some tricks, it can come down to order 2.6. So this is a very expensive operation when n is very large, such as 1 million. Okay, so we don't use Newton's method for optimization of functions of many variables. We use something called pseudo second order methods, where we try to approximate the H inverse using faster methods. The last topic in optimization is constraint optimization using Lagrange variable. Uh, so here we want to, let's say, maximize f, okay, but subject to a condition. So we want to maximize f of x, uh, but it's not unconstrained in the sense that that's not all we want. We also want a condition, okay, subject to g of x is equal to 0, and x could be a variable. So x is bold, it's a variable. Okay. So it's constrained. There's a constraint that gx should be 0. So now let's look at level sets of f of x equal to constant, right? So let's say these are contours like this. Okay. And now let's draw the curve for gx is equal to 0. So let's say that curve is like this. So this is gx is equal to 0. Okay, it could be gx is equal to c, whatever it is, gx is equal to 0. And these are f of x is equal to some constant. Right. So now imagine you want to maximize it, and let's say the maxima, the unconstrained maxima lies here. Okay, this is a bowl that is inverted. It's coming out of the screen. It is curving away from the screen. The center is towards the screen. Now, obviously, you can imagine that this point where this would be the maximum value for which gx is 0. Because if I go to any other point, right, if I go to this point, at this point there is a separate contour of fx is equal to c that goes through this, where the value is smaller than what is at the center. Okay, so it is outside the center, further outside. So how do I ensure that I find the tightest possible, how do I find the tightest possible ellipse of fx is equal to c, where gx is equal to 0? That obviously will be when the two are tangential to each other. Okay, so basically the way to achieve this would be that we will define a new function fx plus lambda gx. Okay, this is your new function lx. Okay, and we'll try to maximize this function subject to lambda being not equal to 0. That's all, right? uh, that's all we need to do. So this is called Lagrange multiplier, and when we do this, obviously what we will do is we'll take its derivative and make it equal to 0. So basically what we'll get is delta fx plus lambda delta gx equal to 0, right? So unconstrained optimization would have been just that delta fx is equal to 0. Okay, so now for this entire vector to be 0, what is needed is that the direction of gx is delta gx is parallel to the direction of delta fx. These two have to be parallel so that both, or three components or four components, all components cancel each other out, just because of some lambda. Okay, and that is the precise condition for having a common tangent, or in other words, having a common normal. Okay, or parallel normals. Right. So for that, we want this to be this equation to hold true, and this will solving this equation